The rapid expansion of low Earth orbit satellite constellations has transformed noble gases into critical strategic assets. Xenon and Krypton serve as the primary reaction mass for high-efficiency electric propulsion systems. Because these gases exist only in trace atmospheric concentrations, their recovery is entirely dependent on cryogenic air separation units integrated into large-scale steel mills. This structural coupling makes the global supply of satellite propellants highly inelastic. Global xenon production is capped at approximately 12.5 million liters annually. Meanwhile, space sector demand has scaled from under 4% of global supply in 2018 to a projected 40% by 2026. This rapid demand growth has created a structural supply deficit. Geopolitical disruptions in 2022 sidelined major Ukrainian purification facilities, causing spot prices to spike from $15 to $120 per liter. The geographic concentration of crude noble gas extraction mirrors the footprint of global heavy industry. China controls 35% of crude extraction and 45% of high-purity purification, leveraging its massive domestic steel manufacturing base. Prior to 2022, Ukraine purified up to 50% of the world's high-purity noble gases. The conflict in Ukraine permanently shifted these purification nodes to East Asia and the United States. The United States remains highly vulnerable to supply chain shocks. It possesses only 5% of global crude extraction capacity and 10% of advanced purification infrastructure. This domestic deficit forces Western aerospace firms to rely on volatile foreign supply chains for critical defense and commercial satellite launches. Any disruption at East Asian processing facilities immediately threatens domestic orbital deployment schedules. To bypass the physical supply limits of Xenon, satellite operators are forcing engineering and thermodynamic trade-offs. Krypton offers a 90% reduction in raw material cost, priced at $4.50 per liter compared to $45 per liter for Xenon. This economic incentive has driven mega-constellation operators to transition to Krypton-based thrusters. However, this transition imposes severe physical penalties. Krypton requires 15.3% higher ionization energy, measuring 13.99 electron volts compared to 12.13 for Xenon. Its lower atomic mass and storage density demand larger propellant tanks and higher onboard power allocation to achieve comparable thrust. Argon represents the absolute thermodynamic floor at 10 cents per liter, but its extreme ionization energy of 15.76 electron volts restricts its use to ultra-high power deep space propulsion. The limits of orbital logistics are ultimately governed by these fundamental chemical and economic realities.